Hi. So the last time we talked, we were looking for an antiderivative for the function 1 over x. And we know what antiderivative functions do. They find the signed area between the function and the x-axis between some point a and some point x. So we knew the antiderivative function had to look like this. But we were trying to find a better way than having an integral in our function. So we also knew that derivatives of antiderivatives bring you back to the function. So the function we're looking for, the antiderivative, we know its derivative looked like the function 1 over x. So from that, looking at the derivative, we could figure out what the shape of this function is that we're looking for. And we saw that it had to be increasing and concave down. And that shape made it look a lot like a log function. So temporarily, we just called it the natural log of x. But it'd be the natural log of x, the whole family, plus some constant. But the actual natural log function, or any log function, when you plug in 1, you get 0. So it has to go through the point 1, 0. So we picked the particular member of the family, the one that goes through like this. So we call this the natural log of x, and that's when a was equal to 1. And then often you use a different dummy variable so it doesn't get confused with x. And now when you plug in 1 for x, you do get 0 for your signed area. So anyway, that's how we got to the natural log of x. It looked like a log, but we weren't so sure that it really was a log function. But going back to the definition of what the log is, it's an infinite Riemann sum. We tried some values of x and tried to see if the properties of logs held out for this particular definition. And if we put in a and b, we found out that the log of a times b was equal to the log of a plus the log of b when it was a natural log from this definition. We just did it with an example, but we looked it up and found that the math gods actually went back and used the definition of an infinite Riemann sum to prove that all the properties of logs are held by this function. So not only did it look like a log, it really was a log. So we could actually call this the natural log of x, but we knew it was a log base something. So I repeated that because it's kind of a hard thing to really understand where this antiderivative of 1 over x comes from, and then it turned out to be a log. It's quite an amazing thing. So I would really like to find out what that base is. So to do this, I'm first going to give just a quick review of inverse functions. So what do inverse functions in general do? If you have a regular function like f, it takes a point a that you plug into it and turns it into f of a, which we often call b. Now, what the inverse function does, very simply, is to take whatever b is and does its thing to turn it back into a. So if you think of it, if you took 2 and put it into x squared, you get 4. So what takes 4 and turns it back into 2? And it's the square root function. So the square root function is the inverse function of x squared, the square root of x. But you have to be a little bit careful, because if you took the full domain of y equals x squared from negative infinity to infinity, you get both the point 2, 4 and negative 2, 4 on it. So the inverse function would have 4, 2 and 4, negative 2. So it would no longer be a function. You'd have x values that had two different y values. So to really have an inverse, a function has to be 1 to 1. So y equals x squared does have an inverse, the square root of x, but only if you define it on the domain from 0 to infinity. So y equals the square root of x is the inverse of y equals x squared on the domain from x equals 0 to infinity. So not only does every x value have to have one y value, but every y value has to have one x value for a function to have an inverse. It's called 1 to 1. X and y are in a 1 to 1 relationship. It has to pass both the vertical line test and the horizontal line test. So, coming back to where we're to the logs, does this new function, the natural log of x, have an inverse? Well, it is 1 to 1. Every x value has one y value, and every y value has one x value. So it must have an inverse. And we kind of know what inverses do to logs in general. What if you have the function log base 10 of x? What does it do? You put in 100 for x, and it finds out the power of 10 that gives you 100. So it would come out with 2. If you put in 1,000, it would come out with 3. So what does just the opposite of that? What do you put in 2 and you get 100? You put in 3 and you get 1,000. That would be the function y equals 10 to the x. So exponential functions are the inverses to log functions, which means that our new function, the natural log of x, log base, what we're calling box of x, must have an inverse function. And the inverse function would be box to the x. We just don't know what that box is. This has been the elusive thing we've been trying to find in the last talk and in this one. Well, let's just look what this function must look like. If it's the inverse to this, 1, 0 would become 0, 1. And basically, everything reflects along y equals x. So you'd get something that looks like this. As if you remember from algebra, that's what exponential functions look like. Anything to the 0 power is equal to 1. So it always goes through that point. So this function right here is y equals box to the x. Well, besides these 2 points, there's a point 1 something. 1 what? Well, if you put 1 into here, for x, you get box. Box to the first. So this red exponential function has the point 1 box on it, which means there's a point that reflects over here that's called box 1. And because it's on the natural log function, that means the natural log of this box must equal 1. Well, maybe we can figure out what the box is, because the natural log of x is the integral from 1 to x, so that the natural log of box would be the integral from 1 to box of 1 over t dt. And we know that that has to equal 1. So what I did is I got out my graphing calculator and did some integrals. Now I could look from my picture and it looks like the box is approximately 3. So I plugged 3 And when I plugged 3 into here, I got approximately 1.09. So I knew it had to be a little bit less than 3. So I plugged in 2. And I got 0.693. So I knew it had to be somewhere in between 2 and 3. I tried 2.7 and I got very close, like 0.93. I'm getting really close to 1. So I just decided, I don't know where it came from, but I tried 2.7182818. I plugged that in, and I got 0.999999998. And I was going to say, oh, that's good enough. But then I noticed on my calculator there was this little button E. And when I plugged E in, I got exactly 1. So I figured that's why they put that button on there. And so we found out that the function is really e to the x, and the base that we were looking for of the natural log is this number e. And I looked it up, and it's an irrational number. It's 2.718281828, but it doesn't keep repeating that. It's an irrational number, much like pi is. So anyway, we have this new function now. And the new function is f of x equals e to the x. So in the last 2 talks, we've come up with 2 interesting functions, and they're inverses of each other. So now that I've got this new function, I would like to be able to find its derivative. Well, I tried going back to the definition. I said the derivative is going to be f prime of x. It's the limit as h approaches 0 of f of x plus h, so e to the x plus h minus f of x all over h. And I knew that the answer to that would give me the derivative, but there was no algebra I could do to simplify that. So I had to cross out that way to figure it out. So I had another thought. Maybe there's some connection between derivatives of functions and derivatives of their inverse. Because we know the derivative of the natural log of x to be 1 over x. So I went back to a general thing. How do I find, if I have y equals f of x, is there some relationship between the derivative of the function and the derivative of the inverse? So what I did, to both sides, I said, if this equals this, then f minus 1, the inverse of that, should be the inverse of this. Well, the inverse of a function brings you right back to x. So e to the natural log of x equals x. The natural log of e to the x equals x. The square root of x squared equals x, as long as x is positive. So, we have, I'll just write this a little nicer, we have x equals y. And now I decided to take the derivative of both sides with respect to x. So the derivative of x with respect to x is 1. And what's the derivative of this? Well, it's f minus 1 prime, so the derivative of f minus 1 of y. So we have to do the chain rule because this is not x. So we have to put y in for x and then multiply by its derivative, which is y prime. Well, y prime is dy dx. So dy dx, or f prime of x, is equal to 1 over the inverse of y. It's derivative. Maybe I should write that just a little better. 1 over f minus 1 prime of y. And it's a little complicated. It looks like it's just a reciprocal, but notice it's not at x, it's at y. So if you go over here, these two places, E1 and 1e, this slope here is going to be the reciprocal of this slope here. This is a reciprocal relationship. Well, the reason I did this, by the way, this is a nice formula in itself, but what can I do if y equals e to the x? What if I want to find its derivative? I can say its derivative is 1 over the derivative of its inverse function. Well, the derivative of its inverse, the natural log of x, is 1 over x. So it would be 1 over x, but it's not at x, it's at y. And y is e to the x. So the derivative is 1 over e to the x, or e to the x. It's a little bit complicated here to derive this, but it's a wonderful outcome. We now know that the derivative of the function e to the x is e to the x. This function e to the x, its y value is the same thing as its slope at every point. So right here, when the y value is e, the slope is e. And we can kind of show what's the derivative of the natural log of x? It's 1 over x. So at the point e comma 1, the slope is going to be 1 over e. It's the reciprocal of e. And I didn't leave myself that much space, but what's the antiderivative? If the derivative of e to the x is e to the x, then the antiderivative of e to the x is e to the x. But I want this to be a new formula. So I'm going to make it e to the u du. And I've got my number 9 as far as forms of antiderivatives that I know how to do. I've got the new one we did for du over u. We've got u to the nth du. We've got those 6 trigonometric forms, and now we've got this new 9th form that we can take antiderivatives for. So there's quite a bit here, but really nice outcome. So let's try to do some problems. These will actually be easier than all this theory that shows why it works. Say we have y equals e to the 2x plus 1. Find dy dx. What is it going to be? Well, the derivative of e to the x is e to the x. But that's not x, so I have to do the chain rule. So the derivative is e to the g of x times g prime of x. And g prime of x is just 2. That's it. Use the new formula, which is a real easy one to remember, and never forget the chain rule. Now, on this one, you could do the exact same thing with a chain rule. You could say the derivative is e to the natural log of x times the derivative of the natural log of x is 1 over x. But I would suggest, since e and the natural log are inverse functions, you can call e to the natural log of x just x. So you get the derivative of x is just 1. And that's the answer. Now you might say, why didn't we get the same answer? Well, you really did, because e to the natural log of x is just x. And x times 1 over x is 1. So keep in mind these relationships. These are inverse functions. So if you get e to the natural log of x, it's just x. And if you get the natural log of e to the x, it's just x. Okay, let's try one more derivative. This one, to find f prime of x, again we have to do the chain rule. So the derivative is e to the this other function, then times the derivative of this other function. Well, it's x plus 1 to the 1/2. So it's 1/2 times x plus 1 to the negative 1/2. And then times 1 if you want to finish the chain rule. So altogether, it's e to the square root of x plus 1 all over 2 times the square root of x plus 1. So if you want to find f prime of 3, what is it going to be? E squared divided by 4. You actually get since you're finding the derivative at a number, you actually get another number. E squared over 4 would be like 2.718 squared divided by 4. So really, derivatives of this new exponential function are quite easy. And as you might have guessed, exponential functions are something that show up a lot in real-world situations. Just think of exponential growth, which we'll talk about more later. Okay, now, antiderivatives are a little harder to take. So here's an indefinite integral. Well, what form could it possibly be out of the 9 forms? I bet you it's this new one, e to the u du. Well, to make this e to the u du, we've got to make this u. It's about our only choice. So what is du then? 2x plus 6 dx. So I just start rewriting it and hope it works. Right there, I can call that e to the u. And what do I have left? X plus 3 dx. Well, I could write this 2 times x plus 3 dx. So x plus 3 dx is just 1/2 du. And the antiderivative of e to the u is e to the u. But I don't want to leave it as u, so I put it back as x squared plus 6x. And then it's an indefinite integral, so it's that whole family of functions that's your answer. So I think we will shift over now to the other board and just do 6 more problems. And we are getting close enough to the end of the chapter that I've actually brought a few things from earlier chapters in that we should be trying to remember. Not this first one. This first one is just a definite integral, and I think it's going to use the new form that we learned. Do you think you can see the possibility of getting e to the u du out of that integral? Well, if I'm going to, the only way I can possibly do that is if I let u equal sine of x. Then all of this I can call e to the u. The 5 I can write out front. And what is du? Du is cosine of x dx. Exactly what I've got left. So that one actually worked out quite nicely. This whole thing just turned out to be 5 times e to the u du. 0 becomes the sine of 0. And pi over 2 becomes the sine of pi over 2. What's the antiderivative of e to the u? Just e to the u. So you get e to the first power minus e to the 0 power. And any number to the 0 power is just 1. So we have an answer. Now, don't forget, if we want to find dy dx, we don't always have to have the function solved for y. Like this one. I've got a y here and a y here. I don't think I can solve this for y. So what do we have to do to get a derivative? We have to solve this implicitly, which means we just start taking derivatives with respect to x. So the derivative of e to something is e to something, but then when that isn't x, I have to multiply by its derivative. Well, what's the derivative of x times y? We've got to use the product rule. So we go the first times the derivative of the second plus the second times the derivative of the first. And the derivative of y with respect to x is dy dx, or y prime, and the derivative of 2 is 0. So our goal is to find y prime, but we only have to find it at x equals 0. So maybe we don't have to solve this for y prime right now. Let's plug in the values. The trouble is they didn't give us the y value. But if we go back to our original relationship here, if I plug 0 in for x, I get e to the 0 plus y equals 2. So y must equal 1. And now I can put 0 in for x, e to the 0 is 1, 0 in for x again, 1 in for y, and I've got a pretty easy thing to solve for. Y prime is just going to be -1. So that's the slope on this curve from this relationship at the point 0, 1. So that's a little bit of a review of implicit differentiation. Okay, we've got another indefinite integral. And as soon as you see e in there, you're thinking maybe it could be e to the u du. The only way it can be is if that equals u. So it's x to the -1, it's minus x to the -1. So du is -1 times -1 is 1, x to the -2 times dx. So this one works out super. That just becomes e to the u. And what is 1 over x squared dx? That's just du. So it's exactly in the form of e to the u du. So the antiderivative is e to the u plus c. And then you just put your u back in, and you've got your general family of functions. Okay, so find the minimum value of this function for x greater than 0. Do you remember what we're supposed to do when you're looking for maxes and mins? We look for critical values of this function, where the derivative is equal to 0 or undefined. So the first thing I have to do is take the derivative. And I've got to do the quotient rule. So I go low, d high, the derivative of e to the x is e to the x, minus high, d low, the derivative of x is 1, all over low squared. And I can factor out an e to the x. And then we often on the number line put our derivative. And this is only for x greater than 0. Well, the nice thing about the function e to the x, we know from the graph that it's always positive and never equal to 0. So only at x equals 1 can you get a 0 derivative. And it's never undefined because x equals 0 would make it undefined, but that's not in our domain. So the only critical value is 1. And if I take, knowing that this is positive and this is positive, I know it's going to be negative until you get to x equals 1, and then it's going to be positive. So if you look at it, the function itself does this. It goes down, and then it goes up. So the minimum value is going to be at x equals 1. We can see right from there. That doesn't quite answer the question. It wants the minimum value of the function. So that's going to be f of 1, which is e to the 1 over 1. So there's our answer. That's the minimum value of that function for x greater than 0. Okay, now another thing that we did not too long ago is find the area between a curve and the x-axis. Well, this one's only between 0 and 1. And if I put in 0, I get 2 over 1 plus 1. So I get 1. And if I put in 1, I get 2e over 1 plus e. We know it's positive. It doesn't really matter if you've got it perfectly done. All we need to know is that it never dropped below the x-axis. And to find area, I put in my rectangle. And then I just say the area equals the integral from 0 to 1 of the height, which is the function value, times the width, dx. Now I'm seeing that and I'm thinking, oh, we just learned this e to the u du. But there's no way I can really get this in the form of e to the u du. Letting u be x is never going to help us. But is there another one of those 9 forms that I know? Well, whenever I see a division bar, I'm thinking it could possibly be du over u. I can possibly get it into the form of du over u. In order to do that, I have to let u equal 1 plus e to the x. In which case, du is 0 plus the derivative of e to the x is e to the x dx. So when I go to rewrite this, the bottom all becomes u, the e to the x dx becomes du, and the only thing I haven't taken care of is the 2, which I can put out front. 0 becomes 1 plus e to the 0. So that's 1 plus 1 or 2, and 1 becomes 1 plus e. So we've got our integral into a form that we can do it. The antiderivative of du over u is the natural log of the absolute value of u. So I get the natural log of the absolute value of 1 plus e, which I really don't need an absolute value sign because it's positive, minus the natural log of the absolute value of 2. And that's going to be your answer. All that, if you put it into a calculator, would give you a number. And it'd give you the area between the curve and the x-axis. So, let's do one last problem that finds a tangent line to the graph of e to the x cosine of x at x equals 0. Well, to get a tangent line, we need a point and a slope. Well, 0 is the x value. What's the y value? E to the 0 cosine of 0. Both of those things are 1. So there's our point. What's our slope? Now we have to do a product rule. It's a function times a function. So we go the first function times the derivative of the cosine plus the cosine times the derivative of e to the x, which is e to the x. And I'm plugging in x equal 0. Well, the sine of 0 is just 0. The cosine of 0 and e to the 0 are both 1, so the slope just turns out to be 1. See, the equation is y minus the y value equals 1 times x minus 0. Or just basically y equals x plus 1. That's the tangent line to this seemingly complicated function at x equals 0. So, took quite a while today. I think you see the problems weren't as hard to do as the theory as to what this function e to the x is and how it's the inverse of the natural log of x. But we're going to use those two functions a lot. So, have a good rest of your day.